integration by substitution. So we have to reverse the chain rule even when things have been simplified. This is the key thing here. We'll know that the chain rule was used when in the thing that we want to integrate, we notice a function and also the derivative of that function being present. So we have to notice that there was a function inside of something else and its derivative is also there. We did some of these when they worked out perfectly and easily. This was a question in your chain rule notes in derivatives. This one, we see 3x squared plus 5x as an inside function. Its derivative is right there. The outside function, the 5 came out in front, subtracted 1 from the exponent, kept the inside the same, multiplied by the derivative of the inside function, and we get that y equals 3x squared plus 5x to the 5. And of course, there could have been a plus c. This worked out perfectly fine because of how it was written. The question will become is, we will be asked to do this same one when somebody did this. You see what I did? I just took the 5 that was out front and I distributed it in the 6x plus 5 and got 30x plus 25. And we'd have to be able to undo this when someone simplified something. And the key will be, can you recognize an inside function? Oh, I have a 3x squared plus 5x inside of the power of 4. What would the derivative of that inside function be? Well, exactly, it would be 6x plus 5, but more informally, it's a line. Because it's a line, and this is a line, there might be a chance that we could integrate. But it's not as easy as it was originally when it was broken up nicely. And that's what's going to make working backwards with integration sometimes harder. Now, we won't start off with a super hard one right away. We'll start off with some more straightforward ones. These will all be ones where we integrate by substitution. And what we're going to notice as a technique, we're going to take out our highlighters. We're going to highlight an inside function in yellow, and maybe even here. We'll write the word inside to get us thinking about the original function needed to be an inside of something else, and then its derivative in green. So for example, in the first one, this is not yellow. In the first one, oh, just checking, because it has happened in the past. Does anybody have colorblind issues to yellow highlighter? It's true, I had a student, yellow highlighter on white was the same as for a person who wasn't colorblind as using a clear highlighter. It did nothing on the board. It was like, you wouldn't see that yellow at all, it would just be clear. So I'd be like highlighting stuff all year and they're like, it's not working. So, but I changed to green or purple highlighters, they were fine. So there is the function that's inside. Notice I didn't just highlight the x squared, I highlighted the entire inside function, and there's its derivative. x squared minus 3x is inside the cube root. And there's its derivative. Number 3. That is technically, you could think of it as inside an x to the minus 1. This would be a logarithm, like, when you see this question, when you see the answer to this, there's like nothing in your mind was like screaming logarithms at this moment. The integral of this one will have logarithms. And it's going to be hard to see that. The derivative of that one is right there. Okay, I'll let you do the next 5. I'll show the answers in a bit. You're looking for the original function, an inside function, highlight that in yellow, and then find its derivative in the same one, highlight that in green, or whichever colors you chose. All right, let's see how you did. And there's one typo. Did you notice this one was missing a dx? I'm sorry, I'm in a good mood. It's like, if you didn't know, feel like you didn't notice it was missing a dx, you should drop the course now. Or not. Okay. These are fun. But that usually also means that they're challenging. So we're going to learn a technique for these. And it's actually worked out perfect because we just learned the chain rule in advanced math today. And it goes with the technique that you want to ignore when you're doing the chain rule. Like in the chain rule, I don't know if you remember because it's been a while, but we did a technique that we said this technique sucks and we're never going to do it. And we need to have that for integration by substitution. So a little reminder about the chain rule and the technique that we ignored because we do use it in substitution. So what we do is we will replace the inside function with u. We will make u equal to the inside function. So we're going to have to recognize what's our inside function. And then if u is equal to our inside function, then the derivative du dx of this is just g prime. And this is where Leibniz notation is brilliant. Or, yeah, it's, so mathematically, du dx is a derivative. It's not a fraction. It's a thing. But you're technically not allowed to do this, but it works. Okay? You can't just take part of something that means one thing and move part of it to the other side. Except it works in this case. If we think of du dx as a fraction, we can multiply both sides by dx, we can replace the g prime dx with just a du. And then the f of g of x, because the g of x gets replaced with u, we get fu. Ready? We're good? No. So, here's our first one. We want to integrate this. What makes these not as easy, right? We started off with just the working backwards. The working backwards one I gave you with the chain rule, everything matched up perfectly. Oh, there was a 5 in front, that came the 4, everything matched up perfectly. What happens with integrations is they match up mostly perfectly, except something is missing. And your brain might be able to do this one directly. That's great. Maybe you can see that this is x squared minus 7 to the 5 divided by 5 plus c. Perfect. But often, because there's a lot of little changes that happen, we do need to use a technique. So the technique looks like this. We recognize the inside function is here, and that's not yellow. We recognize the inside function is here, and its derivative is here. So we let u equal our inside function. Then our derivative du dx is our derivative, but we put the dx on the other side because we multiply both sides by it, would be 2x dx. And so this, in the green box, is all of this in the green box. And this, in the purple box, is our inside function right there. So now we do the substitution. We now connect the integral. Instead of writing x squared minus 7, I write u, still have the exponent of 4, and instead of 2x dx, I now write du. And what our substitution has done is changed our complicated thing into one of our easier integrals. This is just a power rule. How do you do an integral for a power rule? It is add 1 to the exponent, divide by the exponent, plus c. Perfect. So now what do we do as our final answer? Once we've done the integral easy with u, you can now substitute back. U was x squared minus 7. And we would have x squared minus 7 to the power of 5 divided by 5. You can check, take the derivative of that. You see that your 5 would come out in front and cancel with the 5. Subtract 1 from the exponent, you get a 4. Multiply by the derivative, it matches up perfectly with what we had to begin. Again, this one might have been one that you could have done in your head. but the substitution just makes things easier. And the more complicated, like we had to divide by 5, but the more complicated the numbers are in front, the harder it is for your brain to hold everything. The substitution works really nice. Okay, I think you can try this one on your own. All right, I'll check this first one. Let u equal the inside function, and the derivative will be 2x minus 3 dx. And we can rewrite this as u to the 1/3 du. So I multiply by the reciprocal to get rid of the fraction inside of the fraction. That gives me 3/4 out in front. Add 1 to the exponent. I think this is a great example. As soon as your exponents start to go to fractions, now your brain is trying to, if you try to do this one directly, it's a little bit hard. But the substitution still makes it relatively easy. You did on this one, you would let u be the inside function, which is sine x. The derivative of sine x is positive cos x dx. And this becomes e to the u du, which is equal to e to the u plus c, which would then equal e to the sine x plus c. No, I made a mistake. I forgot a negative, right? Or no? Now I'm going, no, because the derivative of sine is co. I'm good. Oh. Or did I? Oh, where's the 5? I didn't. That's easy to fix. There. The 5 would be. This is where if you go back to your coloring, you're always letting u be an inside function. In this case, the inside function is hard to tell because it's on the bottom. So you could say, oh, it's inside because it's on the bottom of a fraction, or you could think of it inside a -1 exponent. There's our derivative. So when we rewrite this, the whole top is going to become du, but you'd still have a 1 on top of your fraction. They just all left? I want to make that announcement. All IB math students, please return to class. you done this one already or not yet? Yes. Does everybody have a chance to try this one? Okay, try this one. And then I want to do H together. With H we can have some interesting things happen. Just going to the answer directly?
Well,
So you'd have to divide by 2 because of that, yes. Squared. Yes. Now, can you do H, but do the substitution a different way? Like you let U equal sine 2x, and let U equal this. Let U equal cos 2x and see what you can do. Okay, for this one, oh, this is the one that was missing the dx up top. Did you get the negative? Worked. Now I wanted to do H together because you could think of this as the derivative of sine is cos, but the derivative of cos is also sine. So what you choose as your inside function and your outside function could actually change in this one. The nicest way to do this question is if we let, split the page up, we'll do it 2 different ways. If you let u equal sine 2x, then du would be cos 2x times by 2, because you have a chain rule, dx. Do you see that part? That the derivative of sine 2x is cos 2x, but because of the chain rule you have times 2. But we don't have an extra 2 in our equation. So what we have to do is divide both sides by 2 so that this matches up perfectly with this. Substituting back in gives us the integral. Instead of sine 2x, I write u. And instead of cos 2x dx, I write du over 2, which is the same as that I could have that 1/2 there, or I could even bring that 1/2 out in front. How do we integrate u to the 1? We would add 1 to the exponent and divide by 2. Plus c. So we will get 1/4 u was sine squared x plus c. Method 1. How many fun methods should we do? I'm going to do 3 fun methods for this one. You could also have decided to let u equal cos 2x. Then the derivative of cos 2x would be negative sine 2x times 2 because of the chain rule dx. And to do the substitution, check this out. I'm going to put this sine 2x in a green box. I'm going to put cos 2x in a purple box. here's my cos 2x, and there's my sine 2x dx. So if I did this substitution, I would get the integral of u times du over negative 2. Which is the same as a negative 1/2 u du. Integrating this, we would get negative 1/2 u squared over 2 plus c. And our final answer becomes negative 1/4 cos squared x plus c. And that answer does not look exactly the same as the first answer. And yet it is also right. Is that a little problematic for you? I hope so. Good. Welcome to integration. Method number 3. So we are figuring out I'm going to hide one step, and I'm going to write the next step. What is the step that's missing? What the heck did I do? The step that I didn't show you is that in front of this sine 2x cos 2x dx, I added a 2.5, which does nothing, supposedly. Right? Because if I multiply by 2 and multiply by 1/2 really quickly, I just multiply by 1. The reason, though, that I did that is what's in the green brackets is one of your identities from last week. 2 sine x cos x is equal to sine 2x. So I could replace, my alpha would be 2x, and I could replace this whole thing in the green brackets with 2 times 2x, which would give me sine 4x. And now I have an ax plus b question. I don't even need to use substitution. The answer to this one would be as follows. Integral of, well, the 1/2 would still be there. The integral of sine is negative cos 4x, and because of the chain rule, I'd have to divide by 4 plus c. So here is another answer that is also correct, which looks nothing like the other 2 answers. So my recommendation on your test is when you don't know, write down any answer and just add a note, well, by the way, Mr. JR, I used a technique that you don't know about. And it's right. But it probably won't be right. But it's a good try. Because now we got 3 different answers for this one, depending on which technique we used. All right. Now we get into the more complicated. Well, this more complicated one is similar to the one that we just did. We'll leave these other ones for next class, but I just wanted to point out in our first technique, which is probably the best one, Because we had this chain rule with an extra 2, we had to divide by 2 to make it match up. The same thing is going to happen, you can try it on your own, in this one. Things don't match up perfectly, but the inside function is a 4x squared plus 1. Its derivative is an 8x, but we just have an x. But as long as you have the right form, the number in front, you can manipulate to make it work. But that's why the substitution technique is really important, because it gets to be too hard in your head to manipulate all of that all at once.